Hello, students. I will be giving you an introductory lecture today on nanotechnology. Now, you might have known that the word nano means 10 to the power minus 9. And if we consider the size of an atom, it is roughly, you can see that it is in meters, 10 to the power minus 8 meters. So it implies that when we go to this dimension, what we are doing actually, we are going into atomic order. It means we are dealing with few atoms now. Now, when we go to such level, what happens is that there are some quantum effects being generated. And these quantum effects, what they do, they drastically change the properties of materials. So let us take an example. The change in property actually takes place in every aspect. There can be a change in property in mechanical, there can be a change in electrical and electronics property, there can be change in optical property, surface properties of materials, so on and so forth, you name it. So everything is happening because of this quantum size effect that is being developed due to going into this atomic order. Now, before going into nanotechnology, we would like to know what do we mean by a nanomaterial. When would we say that a material has gone into nano dimensions? So, this right here. What do we mean by this? Now, we know there are three dimensions in nature: X, Y, and Z. Now, out of these three, if at least one of them goes to this nanometer order, by going into nanometric dimension doesn't make it a nanomaterial. First of all, this is a misconception that anything that goes to nanometer would make it nanomaterial. Apart from going into this dimension, it should also show the quantum effects or the nano-sized effect that we talked about. So there are two conditions. First of all, it should go to this nano dimension. Secondly, by nano dimension, I mean 1 to 100 nanometers. There is some controversies regarding whether we should call it 1 to 100 or 1 to 500, but basically we take a standard and we see that nanomaterial is usually found in this dimension, 1 to 100 nanometers, and it should be showing this quantum effects. Now, in this 3D material, there is something called density of states. That means when the material is not a nanomaterial, it's a bulk material, it's a normal material, then the electrons in the material can go to any of this X, Y, and Z direction. So the freedom or degree of freedom, I should say that, degree of freedom is 3. Whenever we are restricting any one dimension, so out of these 3 dimensions, suppose in one dimension we are going into nanometric order. So by going into nanometric order, as we have said, that it is showing some quantum size effects, and we get something called a quantum confinement. We'll get to know these mathematically what do we mean, but for the first class, understand that it is a way that we are restricting this free movement of electron. So as we have got a degree of freedom, similar to that we will have a degree of confinement. And it is now 1 for this material, so we will call it as DOC, DOF in this case, and this is DOC. So in this case DOF is now 2 and DOC is now 1. Now what happens when we go to, so this dimension is nanometer. Now we go to another dimension, we also make it a nanometer. So the first case, it was a one-dimensional confinement, or the degree of confinement was 1, and it was a two-dimensional material. So like if this is the bulk and we reduce this dimension to nanometer, it will look like this. So basically it's a 2D material. So degree of freedom is 2, and degree of confinement is 1. So if you now plot a chart with material dimension, then degree of freedom and degree of confinement. So you can say that if the material is a 3-dimensional material, degree of confinement is 3, degree of freedom, degree of confinement is 0. We have a 2-dimensional material, then degree of freedom is 2, degree of confinement is 1. If we have a 1-dimensional material, then degree of freedom is 1, degree of confinement is 2, and lastly if we have a 0-dimensional material, degree of freedom is 0 and degree of confinement is 3. You might be surprised to know that there is something called a 0-dimensional material. Now we will explain each one of them. Now 2-dimensional I will already explain. This is called a thin film. This 2-dimensional material is called a thin film, where nanometric degree of freedom is 2 and degree of confinement is 1. Now the next come if the confinement is done in 2 dimension, like in this case. So if we confine again in another dimensions, it will be like a wire. So we call this one as a nano wire, in short NW. Here the degree of freedom will be only in one dimension. This is where the electron can move freely. So degree of freedom here is 1 and degree of confinement is 2. And now if we again make whatever available dimension also to nanometer, if we make this one also, we also reduce this one to nanometer, then what we get is a very small material which is where the degree of freedom is 0. That means electron is confined in all the 3 dimensions. So, and the degree of confinement is 1. So this is what we actually mean by a 0-dimensional material. This is a 3-dimensional bulk material that we see in everyday life, and this is a 0-dimensional material, and we call this material as a quantum dot. So it's called a quantum dot, where the degree of confinement is 3. Sorry, this is 3. Okay. So this is the basic understanding. Now, as we have as I've told in my last slide, that there is something also called density of states, which is very important. Density of states, and it is very important considering the quantum mechanical aspects of nanomaterials. Now, what do we actually mean by density of states? It simply means that number of states in a particular energy level. Now, this density of states is very important while we are trying to understand the nanometric properties. Now, what happens is that due to confinement, that we have already told you, that is due to restriction of the electron movement, the energy, their energy becomes discrete. Energy is not continuous. But actually what we mean by energy is, now suppose let's take the example of quantum dot. We plot the density of states of quantum dots with respect to E, then you will find that it is like this. We have discrete energies. Okay, so this is what we actually mean by density of states, and that is why it is very important. Whereas in the case of a bulk material, if you take the density of states, it will be like this. So this is continuous and this is discrete. Okay, so that is why this density of states is so important. Now, another aspect to nanomaterial is the surface to volume ratio. In nanomaterials, as we are reducing the dimension, when the dimension is getting reduced, what happens is that the surface to volume ratio, it shoots up, and due to this change in properties of the material takes place. Okay. Now, how do we observe a nanomaterial? We mainly observe it under the microscope. Or we can do some structural characterization. like we can use an XRD, we can use spectroscopy. There are a lot of different types of spectroscopy available. So one is your macroscopy, another is your spectroscopy, and this is basically using diffraction to find out material properties. X-ray diffraction. You take up these one by one, and you can also have something called a nanomaterial in a liquid, and those are called colloids. Or you can also have something called ferrofluids, that is nanomaterials in solution or suspension on the liquid state. You can have also nanomaterials in gaseous state, they are called aerosols. Now I will give a description below where you can have links to some of my videos which I have previously made, and you will get to know some of the basics of these colloids and some of the basics of these spectroscopy diffraction pattern. I will be posting them, and I will take up each one of them. This was an introductory lecture, so I will take up what are the topics that I have told in this lecture. I will take up one by one and use mathematics and explain it in details in my coming lectures. Thank you.